you see, it's not the same like the basin and range where you live, but it's not the Sangre de Cristo. But the participants were just pointing out some, active deformation zone we have been migrating down to the basin. So this is more or less what we have to handle here. Ok, gente, yo creo que estamos más o menos en horario. ¿Qué les parece si vamos directamente a presentar la última charla de hoy? Y es realmente, bueno, un lujo, un privilegio tenerlo. McCalpin, que como ustedes saben es prácticamente el referente mundial en paleosismología, no solamente por su libro de paleosismología, que es por el cual ustedes mayormente lo han conocido, sino que Jim tiene una vasta experiencia, no solamente en paleosismología, sino también en muchas cuestiones que hacen al peligro sísmico. Así que cuando yo invité a Jim, me dijo, pero yo nunca trabajé en el flat slab, ni trabajé, mi fuerte no son las fallas inversas, yo soy un normal fault guy. Y yo dije, mira, cualquier persona que logró generar o, digamos, compendiar en el capítulo de estructuras compresivas del libro de paleosismología, nos puede dar una perspectiva de lujo de otras cosas que se ven en estructuras en el resto del mundo y que pueden ser de mucha utilidad para entender muchos de los ejemplos que vemos nosotros. Y obviamente también hablar de algunas cosas que tienen que ver con la caracterización del peligro sísmico y la incorporación de los datos geológicos a tal efecto. Entonces, como les decía, la presentación de Jim va a tener dos partes que charlamos hace un rato. Uno, algunos ejemplos, y otra, todo lo que es el cookbook del peligro sísmico. So, Jim, I was just giving a quick introduction of you, and having
yes,
said
I understand
this,
normal fault guy.
Well, I suppose you can get what paleosismología means in Spanish as well.
Sí.
Okay, Jim. So I will pass you the microphone to you, and you can start whenever you want. And you can start to share your screen.
Okay, let me try that and see what it looks like. I have a split screen
I can see that
here. So you may see when I share my screen some extra material. Let's just give it a try here.
Okay.
I have your permission.
I think so. Yeah, you can share, yes. Okay, here it goes.
Okay. So there is some extra material here on the screen, but is that okay?
There's no problem. I mean, you can present whatever you want.
Okay, thank you. Carlos asked me, even though I'm a normal fault guy, to speak on seismic hazard assessment in the intraplate compressive setting. And so, as he explained, the first part of my talk will be about some reverse faults that I have worked on to establish my credentials that I'm just not a normal fault guy, but I have seen some other things in my 45 years of doing this. And the second half of the talk will be about what the seismic hazard analysts do with the field information that you bring them. And it's not always what you might think is logical, but it's what they do. And you should eventually in your careers meet these people and learn about what they do, because that's what happens to your data, whether you know it or not. So let's continue here. When I was in graduate school, there was a famous reverse faulting earthquake in Algeria. It was studied immediately by the French who flew down there from France. A week or so later, the leading consultants in America who were at that time the experts in active fault studies flew over to Algeria. And this is what they saw. They saw the primary reverse fault come to the surface here. There was a normal fault associated with the collapse of this overhanging fault tip. There were multiple flexural slip faults in the footwall syncline. And when the French and the Algerians initially flew over this area in airplanes looking for the rupture, what they saw was this scarp. They never saw this scarp. This scarp was unvegetated because it's a normal fault scarp and it's very steep and it was several meters high. And so you could see this unvegetated thing going across the landscape. This thrust scarp was a rollover scarp that was covered with grass, and it went like this, but it did not remove the grass cover. And so it was hard to see from the airplane. They didn't find this part until the field parties got onto the ground. The one strange thing about this is that there was a depression here between the primary reverse fault and the footwall syncline. There was a river flowing in this, and then the river turned and it flowed northwards towards the Mediterranean Sea. And of course, when this surface rupture formed a scarp across the stream, it blocked it and created a temporary small lake here. And people were wondering, well, what is this topographic depression doing in here in the first place? And you have to realize that the footwall syncline brings up strata of various resistances to erosion. And it just happened that the beds that had been brought up here were more erodible than the beds here. So over the long interseismic part of the cycle, there was ample opportunity in those 10 to 15,000 years, which is the recurrence interval on this fault, for streams to erode these soft rocks in the footwall syncline and develop this small topographic depression. So this was our paradigm, I would say, for what a reverse fault rupture should look like as of the 1980s. Now, we are 40 years later, and we have increased demands for studying surface faulting so that we can quantify the surface rupture hazard using a probabilistic displacement, fault displacement hazard analysis, just like the analysis that we've been doing for 30 or 40 years for ground shaking. Now they want to quantify and make a probabilistic prediction of fault displacement hazards at the surface rupture hazards. So this paper that I'm showing by Nurminen et al. From last year makes a more formal subdivision of the types of deformation structures that come to the surface in a reverse faulting rupture. We have the primary fault here, going over here. That is this one, number 1 in red. And then all of the other colors of faults are secondary faults. And some you can't really decide whether they're primary or secondary. This right here in the yellow color is what I interpret as the leading edge of a thrust tip which has rolled over and advanced outward from the primary fault position. But of course, in the very shallow subsurface, this fault merges with the principal fault. So they call this primary distributed rupturing. I had not seen that term before because before this time, we had primary faults and distributed faults, and now they are introducing something they call a primary distributed fault. Well, I understand what they're trying to say. This fault merges at a very shallow depth with the seismogenic fault. The same is true of this back thrust here, which is in the same color. What are the other things that we see? We, of course, see on the hanging wall anticline tensional faults like the ones at LS-NAM. These are bending moment faults. They are fold-created faults, essentially. And that's this purple bending moment distributed faulting. We also have on the footwall flexural slip faults from tightening the syncline and doing this kind of motion. And these are reverse faults. As you can see, when you do this, you get a reverse fault. But if you tighten the syncline so tightly that it becomes overhanging, these flexural slip faults become normal faults at the surface. Then we have these short little distributed faults in blue. Some of these may be, in fact, tension fissures caused by the severe ground shaking that are rootless. They don't actually connect with anything in the subsurface. Their displacement dies out downward. That is one thing that we need to further subdivide here, because right now this simple distributed faulting, they say is it's not predictable. It cannot be mapped before the earthquake. And that kind of implies that it's ground cracking of a rootless nature that is confined to the near surface soil horizons and the loose material at the surface. And then we have what they call sympathetic distributed rupturing on a structure which is totally unrelated to the principal fault. And at the current time in the USA, we would call this triggered faulting. It's faulting that was triggered by transient seismic waves hitting another fault and inducing a small amount of triggered displacement. But obviously this is not physically connected to the seismogenic fault that created the earthquake. Okay, so I'm keeping all these different structures in mind when I go to Alaska, and you can see it's quite a bit more moisture in Alaska than in the photographs you have been showing in previous talks. But some of the structures are the same. Here is the reverse fault. Like in LS-NAM, it's hard to see this because of the rollover of the tip of the fault as it comes to the surface. This never had a free face. What you see, which is the most prominent thing, as at LS-NAM, is a secondary normal fault, which creates a steep uphill facing free face. But this is a secondary feature. And when the reverse fault tip advances very far over the footwall, the tip of that thrusted quaternary and bedrock material collapses, and you get all sorts of secondary normal faults in it due to the collapse, which don't exist outside of this protruding lobe. So all of these things can be recognized in that first diagram that I showed from the Algerian earthquake. Well, this gave me an excuse when I went here to trench a normal fault, you see, because I'm a normal fault guy. I want to do that. But I realized, there's an opportunity here for me to look at the faulting chronology in this secondary fault and compare it to the faulting chronology on the primary seismogenic reverse fault. They should be the same if you believe the models. Well, it did turn out that way. The dating precision was not what I had hoped for, but we dug 5 shallow trenches and then we tried to correlate the events between them, primarily between this secondary normal fault and the primary reverse fault. You can see multiple normal faults here coming into the floor of the graben. And on the thrust trench, there were 2 strands of the reverse fault in here. This red bed is a paleosol, very well developed B horizon paleosol. And this brown deposit here, which is triangular, is a colluvial wedge. One of the 2 colluvial wedges, there's another one right up here associated with this fault. And so you can see that this reverse fault has cut the paleosol and displaced it from here to here, after which this colluvial wedge was deposited. The chronology from the graben trench said there were 3 events bracketed by these 3 ages right here. And we got the same number of displacement events from the thrust trench, and they were bracketed by these numbers here. Now, these numbers are not very precise. There's thousands of years of uncertainty here, but at least for each of the events, the most recent event, which is the white one, the penultimate event, which is the yellow one, and the third to latest event in orange, those 3 age ranges do overlap. But usually we see unexpected things, at least unexpected to a normal fault guy, when we work on reverse faults. On the southern end of this fault, there was a large landslide at the range front. It looked like the entire range front had collapsed during one of these earthquakes and had slid over this footwall bench. This footwall bench is composed of strata that have been bent to nearly vertical in the footwall syncline, and then it was later eroded off to make a flat bench. And you can see right here, this landslide has progressed about 200 meters out onto the footwall bench. At the back edge of it, there's a large graben. The main fault of this graben displaces the latest glacial moraine by 30 meters. That's a big displacement, but that's not a fault displacement. That's a landslide headscarp displacement. So you can't really do anything with this number to try to estimate a magnitude, because this isn't a fault scarp height. This is a landslide headscarp height. You can see there are secondary landslides that have come off the face of this big landslide block. And if you were to take your backhoe excavator and dig a trench right here, you would find a thrust fault. But the question is that thrust fault the tectonic fault? Or is that thrust fault just the basal shear plane of the landslide. Um, and we had noticed this situation before in California. And here's what they call these things: thrust-rooted landslides. Uh, this is what a landslide guy would call these things anyway. A fault guy would probably call these things landslides caused by thrust faults. It depends on your perspective. But here is a cross section. Here is the seismogenic fault. As it comes to the surface, it flops over. Over here, the granites of the hanging wall have been thrust over the quaternary alluvium, and this whole area of the range front has failed in a landslide. So we have the headscarp of the landslide, we have this kind of pull apart graben of the landslide, and we have the body of the landslide and the toe of the landslide. And so what should we call this right here? Is this the leading edge of the thrust fault, or is this the basal shear plane of a landslide, or is it actually both things at the same time? Uh, you just have to realize this. The landslide guys will call this a landslide plane, and but this the age of this landslide, if you were able to date it, for example, if you could find some charcoal or luminescence datable material right underneath it, the date of the landslide should be the same as the date of the thrust faulting event that pushed this material over the quaternary alluvium. All right, now I'm going to talk about a reverse faulting event that is famous because it had such a high magnitude, magnitude 7.7. This is the Bhuj, India earthquake of January 2001. And this earthquake has become famous because it is widely accepted that there was no surface rupture in this magnitude 7.7 earthquake, even though commonly much smaller reverse earthquakes than that have created surface ruptures. So this was kind of a mystery. How could you get an earthquake so large and not have any surface ruptures? Well, what they really meant to say is there was no primary surface rupture. There were some surface ruptures. There was this one, a strike slip fault. Here's the main shock of the earthquake, and the aftershock show that the seismogenic fault dips to the south at about 45 degrees. So you would expect it down at a depth of maybe 20 kilometers, 20 to 30 kilometers. So you would expect to find the projection of that fault out here 20 or 30 kilometers up dip of the main shock, the epicenter. And there are some faults there, but they are mostly strike slip faults, except for there is a thrust fault right here at the end of this strike slip fault. So I'm going to show you photographs of these things to show what you might expect if you have a reverse fault that's very near the threshold for surface rupture. It's not a huge scarp. First, we'll look at this Manfora secondary dextral fault. This is the longest one right here. Does it say how long it is? Nah, I didn't put that in the caption. And it was a jagged looking thing created of various segments, the white ones going northeast and the black ones going northwest, back and forth. And here's the displacement of a small paleo channel, just decimeter sized displacements. One of the interesting things to realize is that the diagram from Nurminen et al., which I showed in the beginning of the paper, didn't have a classification for strike slip faults trending perpendicular to the seismogenic reverse fault. they didn't have a classification for this kind of fault. Although if they had looked at the Booge rupture, they would have realized that this kind of secondary faulting was the most prominent feature created during the earthquake. Well, this was an interesting day in the field when we were out there looking at this. I spent about a week mapping this fault. The temperature in May, when I was out there, 4.5 months after the earthquake, the temperatures in the daytime were up to 46 degrees Celsius. So it was very hot out here. And there's not much vegetation. And we were looking at this. And when we got up to here, measuring the displacements as we came along, this is a mixture of thrust faulting and right lateral faulting. And then we came up to here and we found a true thrust fault, which turned into, again, when it changed directions, into another dextral fault. And I think this is more primary faulting than secondary faulting. And I'll explain why, and you'll see when you see the photographs. The other thing is, when you go to these countries, at least this was true 20 years ago when I did this, they don't have any LiDAR. They don't have any digital elevation models. They have topographic maps, but the topographic maps for this area had been made by the Geological Survey of India when India was a British colony. So the topographic maps were 50 years old and they had a contour interval of 50 feet. And since this whole area out here is flat, basically there were no contours at all for us to work with. And then the maps were secret. They were government secrets in this part of India because it was so close to the border of Pakistan. So my assisting professor from Bhuj, India, had a copy of these maps, but I don't think he was even supposed to legally possess it. So the things that we take for granted today, you can't guarantee that they exist everywhere in the world. So I made this entire map with a handheld GPS unit. This is what the northern dextral fault zone looked like. It had been slip partitioned. This trace here, which was straight, had all the strike slip displacement on it. And there was a subsidiary thrust fault, you can see it right here, which had all the compressive movement on it. We hear about slip partitioning, but usually not at this scale. These are meters, so these faults were only about 6 meters apart. Here's the pure thrust fault that made what we call a mole track or a tent structure. And we followed this for about a kilometer and a half. And like most leading edges of thrust surface ruptures, it was very sinuous. It looked like a snake with all these lobes that had advanced farther. And then this part right here probably has some dextral movement on it. And then it goes back to pure thrust movement on this. There's my little handheld GPS unit for scale. And for scale back here is a sacred cow in the shade of a tree. Remember, it was 46 degrees on this day. We cleaned off the bank of a small stream that was crossed by the thrust fault, and you can see this is the 2001 thrust fault. It dipped 13 degrees to the south, a very gentle dip. But when you see this vertical part here was a soil horizon known as hard pan. It was cemented into a nearly concrete-like consistency by precipitated pedogenic chemicals in there, including silica and calcium carbonate. So when the bottom of this thrust fault hit the bottom of this hard pan layer, it immediately changed direction. It steepened to nearly vertical, and it created this tent structure, which can be followed all the way around here, or mole track, as we call them in the USA. So here's a diagram of a tent structure, how you pop up the ground surface in a cemented brittle layer due to compression. And there was one geologic contact that we could see in the trench. It was the margin of this channel cut into hard sand, and it came down to here, and the fault had displaced it from here to here. So there was 22 centimeters of net slip right there. And that 22 centimeters of slip came up to here. It hit the bottom of the cemented sand. Then it went very steep and created a tent structure that had, coincidentally, a height of 22 centimeters, exactly the same as this displacement. So the low angle thrust displacement had completely been transformed into nearly vertical displacement in this pop-up structure. As we were tracking this rupture along the ground, we came to an earth dam, which ran perpendicular to the rupture. The earth dam went north-south, and the rupture went east-west. So I'm standing on top of this 2.5 meter high earth dam and can see the sinuous mold track or tent structure continuing along. You can see there's a road right here, and you can see people have driven on the road since the fault was formed, in the 4 months since the surface faulting had formed. So you see that little scarp right there. There's another scarp right here. And it was interesting what the thrust fault did when it came up to the bottom of this earth dam embankment. Here we are standing on top of the earth dam embankment. The fault propagated up to the surface from this level through the embankment and up to here at an apparent dip of 36 degrees between surface and this surface. So usually when thrust faults approach the surface, they decrease and dip and get lower. But when it hit the bottom of this earth dam, it steepened just like it did in the cemented sand in the previous slide. And it came to the surface at a steeper dip than 13 degrees. And the way I interpret that is that the mechanical properties of this earth dam were stronger and more brittle than the mechanical properties of this deposit out here in the playa. And just like happened with the tent structure, when the propagating fault hits a very strong unit, it steepens and dips. So that's the same thing that happened here. Okay, so conclusions for the reverse fault surface ruptures, at least from my limited perspective, and from the 2020 paper of Nurminen, is that the surface ruptures are more variable than normal fault or strike slip surface ruptures. They have, as Nurminen says, they have 6 or 7 different possible expressions, including fold-related faulting, primary distributed, triggered, all of that stuff. The near-surface refraction usually turns the fault plane to a lower dip, so it tries to become parallel to the ground. And sometimes it just bulldozes right over the ground surface, like someone is pushing a pile of dirt with a bulldozer. Its actual surface expression, because it has such a low dip, it's going through the near surface materials for a long way. The rheology of these sediments really controls the surface expression microstructures like the tent structures. These reverse fault surface ruptures are more likely to be blind or to be concealed beneath a fault propagation fold, so that if your trench is too shallow, you'll only expose folded beds. You won't get deep enough to actually see the fault which created that fault propagation fold. And of course, there's not going to be much in the way of a colluvial wedge shed from a fold because it's not steep enough to generate a colluvial wedge. It has a wide variety of secondary distributed faults and folds, and this is really why Nurminen went to the trouble to devise this classification system, because you can't just go out there and measure displacements randomly and throw them all into the same data set. You have to separate them based on what kind of fault you measured them on. Okay, so that is the first half of the talk. Now the second half will be, what do the hazard analysts who do the seismic hazard assessments, what are they going to do with your data? And did you collect the data that they really wanted? Two separate questions. You have to realize that the hazard analysts are obsessed with the uncertainty in your measurements. And they have devised what is called a logic tree. It's a series of parallel equations that have been solved using slightly different input variables to predict the ground motion, which would be out here at the extreme edge, the right-hand edge of the tree. They are going to want to put in the mean value that you give them for fault length, for fault depth, for seismogenic depth, for displacement on the fault, for recurrence interval and slip rate. But they're not going to just run the mean values through their tree. They're going to run several other values in an attempt to capture the range or the spread of possible values for each of your input parameters. And when I started in paleoseismology in the 1970s, they didn't ask for the uncertainties in our field measurements. They took the mean values. But within 10 or 15 years of that, they started asking, well, what is the probability distribution around this mean value you gave us? Because we need to know that to flesh out the uncertainties in our ground motion variables, which are the ultimate output of these equations. So this is an example of what a logic tree looks like, each of which has a preferred or mean value for the dip, the depth, the seismogenic depth of the crust. With these two things, you can get the area, the cross-sectional area of the fault in the subsurface, what empirical relationship you're going to use to calculate the maximum magnitude. Are you going to use the fault length, the fault area, or the fault displacement, its seismogenic displacement in either historic earthquakes or studied and measured paleo earthquakes? What is the maximum magnitude that comes out of a regression equation? So you can see that some of these are field measurements that you make. Some of these are outputs for which technique or which kind of regression equation are you going to use to process these field measurements. And some of these are the results of the equations that you chose to get, for example, maximum magnitude. They're all treated the same in the logic tree. There's a mean value, and this logic tree obviously has many, many branches. The drawing that you are looking at here just shows a single thread that is followed through from step to step. But obviously, there are parallel threads that go off this branch that look just like all these other branches, they expand to the right, and off of this branch, they expand to the right. Um, let's see, well, this is the La Bajada fault. Okay, I'm going to show you a logic tree in a few slides for one of the faults in this study, the Pajarito fault. And that logic tree had 250,000 end nodes here for ground motion on the right-hand side. And you'll see why in a minute. But this is what the hazard analysts want from you. They want a mean value, and they want some either discrete estimation of the uncertainty or variability on that mean value. They don't want an entire probability distribution because they would have to discretize that anyway to run all the parallel equations to be solved. But you can see these weights right here in parentheses. They think there's a 40% chance that this value is correct and a symmetrical 30% chance that it's 10 degrees lower than that and 10 degrees steeper than that. So this is a crude discretization of a symmetrical Gaussian-like probability distribution. You can see they also have three values here, the mean value and two values, one which is 3 kilometers less and 2 kilometers more, and it's asymmetrically weighted, indicating an asymmetric probability distribution. They're going to want these values from you, and they're going to want these alternative values and weights from you. You were the one who did the trenching. You were the one who did the mapping. They're not going to make up these numbers unless you don't give them these numbers. And if you don't give them these numbers, they're going to make them up themselves, having never been to your field area, never seen your fault, never been in your trench, because they need them to run the model. So be aware that they will use their own judgment if you don't provide them the data. And you can see this particular branch here, if you follow it and multiply its probabilities all along the string, the probability of this scenario branch right here is the product of multiplying all these probabilities together. It's a very low probability, but remember there's going to be tens of thousands of numbers out here. And in each one of these things, the assigned probabilities add up to 1.0. Okay, so you're going to get 50,000 outputs here of ground motion predictions on the right, and each one is going to have an associated probability, and then they will be all combined into a cumulative probability distribution. Okay, but geologists who collect this data in the field look at it somewhat differently than the seismologists and the hazard analysts do in the office. Geologists measure recurrence intervals directly in the field by dating paleo-earthquake event horizons on the trench wall. And they do this for as many seismic cycles as they can see on the trench wall. And then they construct a slip history diagram, which I'll show later. And from that diagram, they calculate closed cycle slip rates. So geologists measure recurrence and calculate slip rates. Seismologists do it the opposite. They measure slip rates and calculate recurrence from the slip rates. And you might ask, why do they do that? Well, basically, seismologists don't trust geologists' procedures. Because when we go into a trench and we measure, date the seismic cycles exposed in a trench wall and the time span between them, inevitably the recurrence intervals are not all the same. They yield variable recurrence. So what the seismologists do instead is they measure long-term slip rates from landforms of known age which have been displaced by many seismic cycles. And this gives them a long-term average slip rate. Then they need a long-term average displacement number. This is displacement per event on the fault, and it can be based on historic ruptures. It can be based on the smallest consistent displacement of the youngest landforms if there have been no historic ruptures on your fault. Or they might even base it on the displacement expected for a fault of the length of your fault. But by one way or another, they are going to gin up a number for D average. Then they are going to compute the average recurrence interval for your fault as D average divided by the average slip rate. So for example, if D average on the fault is 2 meters of displacement and the long-term average slip rate is 0.1 meters per kilo year, or 1 millimeter per year, 0.1 millimeter per year, this yields an average recurrence interval of 20K years. And then they assume a standard deviation on this. They'll especially do this if you don't give them the data. And then they will choose the 3 weighted values to put in the logic tree. That's what they will do. What is their justification for not taking your recurrence numbers straight from the trench that you measured and you dated? Well, the seismologist procedure does yield a stable estimate of the mean value over longer slices of geologic time. And if the geologist's recurrence values measured in a trench are wildly different, the analyst really doesn't trust that they can compute an average value for them because the sample size is so small. In the old logic trees, all faults were treated as if they were independent and not affected by neighboring faults. They could be analyzed entirely based on their own record of ruptures. But when a seismologist sees a field-derived recurrence interval from one of your trenches that is very short, in other words, 2 paleo earthquakes that happened close together, which we call a temporal cluster, the seismologists are automatically suspicious that the fault could not have generated enough strain in that short time period to generate another large earthquake. So they think that one of the 2 earthquakes in the cluster was probably triggered from an earthquake on another fault. And to include that triggered earthquake in the recurrence interval series for your fault would be a mistake because it violates the assumption that faults only act independently. Well, this is the way they did it 20 years ago. In the past 20 years, even the seismologists have realized that via static Coulomb changes with ruptures on nearby faults and triggered faulting due to transient seismic waves, earthquakes can be on a fault are influenced by large earthquakes on neighboring faults. This has given rise to an improved behavioral front end to logic trees, which addresses how faults and fault segments interact. And how these things interact are called rupture scenarios. So the piece of a logic tree that I showed you before, which I think is probably, is it this thing? No, it's this thing. This was just for a single fault, assuming that fault was not affected by any nearby faults. But now we know better. So what does a rupture scenario look like? Well, let's see. Okay. Here are 2 rupture scenarios for the same fault. These are the mapped fault scarps, all of these lines. And in this rupture scenario here, ruptures only involve the central part of this fault, the thicker line, and it doesn't bleed off into these various splay faults. So in this rupture, the rupture length is 25 kilometers. That yields a magnitude of 6.7. The rupture stops when it hits these cross faults or these complicated fault intersections. On the other hand, some of the geologists believe that this fault ruptures from end to end every time. Not just the middle, but from the end to the end. So you see this is all thick lines. That rupture, if it occurred, would be 41 kilometers long, indicating a magnitude 6.9 earthquake. And the question is, which of these two rupture scenarios is best supported by the field evidence? Well, I can tell you from knowing this fault, the geomorphic field evidence is that there are fault scarps from one end of this fault to the other, but they're a little smaller and they look a little different on these ends than they do in the middle. The other thing is that all the trenches on this fault were in the middle. They were in this section. They don't actually have any trench data from the ends, so they can't compare the dates of the most recent event, for example, on this scarp as on this scarp. They can only use the geomorphic data. You have to realize it's impractical to expect to ever get the money to trench every 200 meters along the length of a 25-kilometer long fault. No one will ever give you the money to do that. So there will always be data gaps that are going to influence what you tell the hazard analysts. So here, these are two contrasting rupture scenarios. Each of these rupture scenarios is going to be put on the behavioral part of the front end of the logic tree with its own branch structures. Well, it gets worse than that, actually. There are two antithetic faults in this system. This is the main Pajarito fault. These two antithetic faults face the opposite direction. They each have one trench on them. And the dates on the most recent event on these two antithetic faults are not only different from each other, they are different from the date of the most recent event on the master fault. The geologists did not anticipate this result would happen, but it did happen. So now they have to consider the possibility that all three of these faults, the master fault, this antithetic fault, which is the Rendia Canyon fault, and this one, which is the Waje Mountain fault, that each of these three faults is an independent structure and can rupture independently of the other two faults. Well, you can see the permutations here are beginning to expand because now you have three faults which can all potentially rupture together, all potentially be independent, or this one might rupture with this one, but not with this one, or this one might rupture with this one, or these two might rupture together and not trigger this one. The permutations yielded 22 possible rupture scenarios among these three faults, some of which were supported by the field data and some of which contradicted the field data. They were all put in the logic tree. All 22 of these rupture scenarios were put on the logic tree with their own branch structures. So this is what the behavioral front end of the logic tree ended up looking like. The Pajarito fault system containing those three faults. Its probability of being an active fault that is a Holocene active fault was 1.0. It was absolutely definite. It just wasn't sure which of these faults ruptured together. Were they all rupturing independently of each other at different times? Were they all rupturing at the same time, total dependence? Or was it a complex combination of these things? And then you can see they considered whether these faults intersected in the subsurface or not. The two antithetic faults are so close to each other that they might, depending on what their exact dip was, they might intersect within the seismogenic crust, which here is 15 kilometers thick. And of course, they're antithetic to the master fault, which dips in the opposite direction. Depending on what you think the dip of this fault is, the Gwaji Mountain Fault, will it intersect the master fault in less than 15 kilometers or not? So that made two different branches. And here are all the rupture scenarios. And finally, we get to the dip of the master fault. And you should recognize that on the previous logic tree, which was meant to represent only a single fault, it starts with dip. So you can see now in this logic tree, here's the beginning of the single fault part of the logic tree, and all the rest of this stuff is about how the faults interact with each other. I mentioned the slip history diagram earlier. This is where we plot the field data, and from this plot, we can graphically measure the slip rates. So on this particular hypothetical example, there have been two ruptures. Your trench or your geomorphic surface went back to 40,000 years old. That is the length of your geologic record. And in the last 40,000 years, there have been two rupture events, each one with 2 meters of displacement. That's these arrows here. After the event at 35,000 years ago released 2 meters of stress, the interseismic part of the seismic cycle began, and the fault is building up stress from nearly a zero state, and it's building up stress and building up strain and building up stress and strain until it reaches the breaking strain across the fault, and then it has another earthquake event. And I just made, in this example, another 2 meter surface rupture at 7,000 years ago. So it took 28,000 years to accumulate 2 meters of strain on the fault, which was released at 7,000 Ka. This is one seismic cycle, and it's what we call a closed seismic cycle because we have the beginning of it and we have the end of it. So the most recent event, the MRE cycle slip rate, is 2 meters in 28,000 years. Comes out to 0.07 millimeters per year. In the trench walls, we have the very end of the previous seismic cycle exposed. But we know how big the displacement was that ended that cycle. But what we don't know is when did it start. So this is a partial seismic cycle that we have here in this 7,000 years. That's 5,000 years. Okay. And we have another fragment, a part of a seismic cycle over here. But we don't know when this seismic cycle will end, nor do we know how big the displacement will be when it does end. So we can't get a seismic cycle. We can't get a valid closed cycle slip rate from these fragments of seismic cycles at the beginning and end of our trench record. We can only get a meaningful slip rate over a closed seismic cycle. It wasn't always done this way. Let's say, for example, that your trench, the oldest bed in your trench was only 10,000 years on this same fault. You couldn't see in your trench the rest of this geologic history because your trench wasn't deep enough. So now what you have is you don't have a closed seismic cycle. You have a single event fault scarp, which is 2 meters high. You date it as occurring at 7,000 years ago. You don't have the beginning of the seismic cycle that this 2-meter displacement ended. And you certainly don't know when the present seismic cycle that we're in today, you don't know when that cycle is going to end. So you have only 2 fragments of a seismic cycle here. In the old days, people would say, well, look, there has been 2 meters of displacement in the past 10,000 years, in the past 10K years. And they would measure this line right here and call that a slip rate. Well, is that really a slip rate? It's not over a closed seismic cycle. So it's not a true slip rate. It's a pseudo slip rate. Okay? It's a slip rate made from a fragment of a seismic cycle before the event, but you don't know when that seismic cycle started, and a fragment that you don't know when that seismic cycle will end. So it's a pseudo slip rate. It's not a real slip rate. Tomorrow, if the earthquake doesn't happen, the time will advance by 1 year, and this line will change its slope. In other words, if the earthquake doesn't happen next year or the year after that, this pseudo slip rate will go lower and lower and lower and lower. True slip rates never change. They're measured over a seismic cycle that has a fixed starting point and a fixed ending point. So don't get fooled into making a statement like this by saying, oh, the slip rate of this fault is 0.2 millimeters a year because in the past 10,000 years there's been 2 meters of displacement. That's a faulty statement because it doesn't represent a true seismic cycle. What the hazard analyst asked us in the early 2000s, actually they asked us this in the late 1990s, what is the variability in recurrence from one seismic cycle to the next on any given fault? Is it very large, that it's almost like a random variation in length? Or is it very small, such that it looks quasi-periodic, that we have an earthquake on a given fault every 2,000 years, and then the next one happens 2,000 years later, and the next one happens 2,000 years later? They were really curious about this because this is the number that drives the ground motion hazard at the end of the logic tree. Well, we couldn't answer that question because all of our trenches were too small. On the Wasatch Fault, which is what this photo is from, between 1980 and 1999, we dug at least 50 trenches. But they were all across scarps that were only 5 to 6 meters high. So they only exposed the evidence for the latest 3 paleo earthquakes, which means they only could have at most 2 seismic cycles exposed in the trench walls. Well, the hazard analyst didn't consider a sample number of 2 to be statistically significant when predicting average recurrence. So we asked them, how many successive seismic cycles would you like us to expose in our trench walls? And they said 10. And we said, well, wait a minute. The fault that we're working on here, the Wasatch Fault, has an average of 2.5 meters of displacement in each surface rupture. And you're telling us you want us to expose 10 such events? We would need a trench 25 meters deep. And they said, so dig one. So we did. In 1999, I dug the first one. This was the second one, dug in 2003. And they did, in fact, have 7 or 8 seismic cycles preserved and exposed on the trench walls. where we could directly measure the length of the recurrence interval by dating the beds exposed and the event horizons exposed in the trench walls. Has this mega trenching been done for reverse faults? Well, yes. Not your kind of reverse faults with the low dips, but the Japanese in the early 1990s dug this 13-meter deep open pit style of trench across one of its faults in Japan. Here's the cross section. So you can see this trench is 13 meters deep. I'll show you a photograph in a minute. But they have a very steep reverse fault. These kind actually do shed colluvial wedges. They're they're steeper than the angle of repose, so they do create an overhanging free face which collapses and gives you a colluvial wedge. This is what it looked like when they're down in it. I have to wonder what the Japanese safety inspectors thought about this in the early 1990s, but clearly they allowed this trench to be dug like this. The walls are not vertical. They did have to put a little bench in here, but obviously this is like 4 meters between this bench and the surface. And no, you could not legally dig such a trench in the USA today that looks like this. But they got multiple colluvial wedges and multiple seismic cycles in this. Okay, so I don't know if you would ever be allowed to do something like this. And of course, let me see if I mentioned this. I don't. Oh, yeah. Because your faults have a lower dip, this whole story here will be down under the ground, about down in here somewhere. It'll be beneath the hanging wall. And the deepest part of your trench, even on a thrust fault with a 30-degree dip, the deepest part of your trench is going to have to be way back here. Okay, because that's where all the colluvial wedges and the cross-cutting relationships and all the critical evidence is going to be with your lower dip faults. It's going to be in a zone that runs like this. And so you're going to have to, your whole trench and your whole story is going to be from back here. And you have to be prepared if you're thinking about doing a mega trench, how you're going to do that in a safe manner. Okay, so this is the sermon. You can think of me as up in the pulpit of the church now. In each country, the National Seismic Hazard Map, which is a PSHA, a probabilistic seismic hazard analysis product, is produced by analysts in either the National Geological Survey or the National Seismological Observatory. They are the ones that are going to use your data to create hazard maps. So you might as well get to know them. And you might as well ask them, what is the largest source of uncertainty in your hazard map? Does it come from the seismic source characterization part? Or does it come from the second part of PSHA, which is the ground motion prediction equations part? Obviously, we seismologists don't have anything to do with the ground motion part. So if they tell you it's the SSC part, you need to ask them, what can we as paleoseismologists do to decrease your uncertainties? How about locating more Holocene active faults for them to insert into the PSHA as line sources? This is what we want them to tell us. We want them to answer yes for this question, because then that will make more fun work for us. But it will make more work for them, and not necessarily they will consider it fun. So I'm thinking they won't say yes to this question. Well, then we can ask them, well, how about what if we better characterize the faults that are already in your existing logic trees? And they might say yes to that. What about fault-specific measurements that we're now contributing? Which ones contribute the most uncertainty? Is it the rupture scenarios and the behavioral front end? Well, that's data they can only get from us, paleoseismologists. This is a complicated matter and requires paleoseismologists to bring all their skills to bear to make these rupture scenarios. This is the biggest part of the uncertainty in their output ground motions from earthquake timing information, recurrence and slip rate. And if that's true, that means we need to do a better job on dating the paleo earthquakes, not give them age numbers that carry high uncertainties, unless those uncertainties are actually real variabilities in how the system works, and they're not just measurement error uncertainties. And those two things, which are very different in practice, tend to get treated exactly the same way in the logic tree. Or are the main uncertainties in their predicted ground motions from the earthquake magnitude side, having nothing to do with the timing? And that means we need to do a better job on measuring surface rupture length, displacement, and things that generate the magnitude estimates, MMAX, that we're giving them. You'll find that the hazard analysts are not opposed to refining their models to include more real-world complexity. They actually look at this as a challenge that they can do and we can't, because we don't understand the mathematics of their logic trees. But they need our expertise from mapping and trenching these specific faults to know what the real world actually is. So as you go through your careers, find out who these people are and see if they're interested in decreasing the uncertainty in their outputs. Certainly, engineers are interested in this subject because the more uncertainty there is for the engineers in designing critical facilities, the more of money they have to spend to make sure that the building is built safely to withstand even the hazard produced by the tails of the hazard distribution. And the smaller we can make those tails, and the less uncertainty in the entire probability distribution, the less money it's going to cost them to build a safe building. So the hazard analysts are in favor of decreasing uncertainty. The engineers are. It should be because it's their money, and the government regulators should be because it increases their confidence. So we all want to do this, but I think we have to start the process. So that's all I have to say today from here in the McCalpin Ranch in Colorado. It's the middle of summer here, so this is what it looks like. Apologies for the English units here, but you can see this is where the world headquarters is. Here's the elevations of the mountains behind us. And I wish you all good luck in your paleoseismic endeavors for the future. And hopefully, Carlos, we have a few minutes left for questions. Thank you, and I'm going to return my screen back to Carlos, if I can figure out how to do that.
Thank you very much, Jim. It's not necessary. Don't worry. You should click on a green button, which is in the bottom of your screen. But thank you very much for your very insightful talk, Jim. Really, I think we can find several takeaway lessons to home. From the first part, I think the model that you show on the through rooted landslide is something that might apply to some of our broken foreland uplift fronts, surely. And I really appreciate you devoted some time to the slip rate issue, because we precisely were discussing that in the days before. In fact, I have used the same diagram you used, which I think it came from your book. Because here we have several cases. For instance, a fall near Mendoza was estimated with a 5 millimeter per year fall, dating 700 meters terraces. But the main problem is that even top-notch journals are accepting those, those data or those papers. But that's another story. I will open the microphone for participants or people who wants to make questions or comments to Jim. No sé si alguien quiere hacer alguna pregunta o comentario. Aprovechen realmente la oportunidad. Todavía digiriendo. I think they're still digesting your data, your presentation. I have a question, Jim, for your second part. I mean, I agree that, of course, trying to reconstruct the paleoseismic record of, if possible, of the entire Pleistocene is very, very necessary. But if you have just one golden bullet, I mean, if you had the budget for digging a mega trench, like the one you show in the Wasatch, what do you prefer to do? Just to put your golden bullet in just one single site, hoping to find a suitable sedimentary record for dating your earthquakes? Or because I think with the money you invested in that trench in the Wasatch, maybe you can perhaps dig, say, 100 in different chronologies of the Quaternary. What would you suggest? Only one mega trench, or different trenches in different ages of Quaternary deposits along the same fault, of course?
Based on our experience in the Wasatch, we spent a lot of unnecessary money digging trenches that were all looking at the same time span of the geologic record, between about 0 today and 5,000 or 6,000 years ago. And so we had so many constraining dates on those 3 paleo earthquakes that we could throw them all into the OxCal calibration model, and we could really eliminate a lot of those dates as contradicting the other dates, and very much tighten up the precision of the ages on the event horizons. So that was a good thing. But it cost us a lot of money to do that. And we could have refined the ages on those paleo earthquake event horizons for the last 3 events much more cheaply by carefully sampling in the trenches to tightly bracket stratigraphically the event horizons. It would have been much cheaper to decrease the uncertainty that way than to dig 50 unnecessary trenches. The mega trench is your only way really to get a long continuous record of those earlier seismic cycles. The 3rd oldest, the 4th oldest, the 5th oldest, the 6th oldest, the 7th oldest. Where else are we going to get that data? Well, I suppose you could go to, if you could find an old geomorphic surface that was not ruptured by the latest several youngest events, then you would not be starting at the latest event. You would be starting in your trench 2 or 3 events backwards. But I never found such a site on the Wasatch Fault. If I went to an old geomorphic surface, it was also had been ruptured by the latest event and the second latest event and the third latest event. So I couldn't do what you're suggesting, is find a place that hadn't been affected by those very recent events and just the older events. You could do that if you could find the right site.
I can see, because I think the situation in the Wasatch Front, like an Omar Fault front, you have a generous stratigraphic record just by the way of the fault. In our fronts or in our reverse fault, you commonly have a very thin quaternary cover, and you need to look for different strands or different places. So it's kind of complicated to to hit a place where you say, okay, I have here the last 100,000 years of stratigraphic records. Our reverse faults don't show that. You need to look for different places, hopefully looking for different chronologies. For instance, in the Pampean ranges, if you hit the trench with late Pleistocene, the Holocene is missing. I mean, you don't have it. And if you hit a Holocene deformed sequence, you probably hit the basement in the footwall, and that's all. So probably taking advantage of your mega trench proposal, maybe we can keep discussing this later, but maybe interesting to see how to supply instead only one place, different places, trying to find out different pieces of the stratigraphic record. That might be an option, but I understand what you mean.
Okay, that can be done if your average fault position has 3 seismic cycles on it, and then the next older cycle is on a different fault position, and it has 3 seismic cycles, and then the earlier seismic cycles than that are on yet another fault trace. You could dig 3 trenches, and then your challenge will be, you have 3 events in this trench, you have 3 events in this trench. Which one is the common event?
Yeah.
You won't be able to use physical stratigraphic continuity to test that. It will all be on your dating. And that means the dating of the oldest event in this trench has to be very precise, and the dating of the youngest event in this trench has to be very precise, because those are the ones that you're thinking are maybe the same one. And once you establish that correlation, then you know this is event 1, 2, 3, this is event 4, 5, 6. Then in your next trench, you'll have the same problem, but you could do it. These wouldn't be mega trenches. This would be 3 macro trenches. They wouldn't be mini trenches, but they wouldn't be mega either. You could do it that way. It's just that in my experience, the displacements, the last 7 or 8 displacements on the normal fault all happen in the same place.
Right. Yeah, I agree. Plus, we should add the problem that many of our low angle thrusts, they commonly become wedge thrust at the near the surface. So sometimes you get events without colluvial wedges related, because they go the opposite. Sometimes they rupture. I mean, commonly thrusts are blind and then they rupture. In our cases, they rupture, but then they flat and then become blind because they go like wedge thrusting. So you are missing the colluvial wedges, and you get instead a slight frontal monocline that sometimes you can even claim that might be the result of the surface deformation instead of rupture. So reverse faults are tricky.
I will have to make a radical suggestion then.
Sure.
Leave the fault. Leave the fault and transfer your studies to lakes. And look at the lake sediments for signs of strong ground shaking and submarine landsliding in the lake. Uh, Lakes have a continuous deposition record, which is unbroken, and they record every instance of strong ground shaking. The Europeans have made a lot of progress on this lake paleoseismology uh, because they can't work on the fault zones themselves because of their climate, because of the low slip rates and the poor geomorphic expression of fault traces in Europe. But they are finding a lot of evidence for strong ground shaking events in lakes that they had no idea had happened. And the evidence is quite clear from the geophysics and the coring and the dating and the lake basins that multiple lakes will be affected by the same age event, meaning it was not a local precipitation or flooding event, it was a regional thing. And so that is something that we fault-centric geologists tend to forget about. The only weakness to this secondary evidence is you don't know which fault caused which ground shaking event in that lake. There's there's some ambiguity there, but we shouldn't ignore this body of evidence because lakes have a great continuous record of strong shaking.
Yeah, I fully agree. In fact, one of the main lessons we have learned during these decades of neotectonic and paleoseismology analysis here is that we should forget to be a fault-oriented guys, fault scarp-oriented guys, and to pay more attention on the not only the linear markers, but to pay attention to the aerial markers like the form alluvial surfaces, which you can even model through price shear or to balance, and then you can capture much better the signal of cumulative shortening, something like that. But I fully agree with your idea. Yeah.
I knew you were a structural geology guy. And you would bring in tri-shear somehow to this discussion.
That's right. Well, I can let you know later, but yeah, it's something that it's kind of rewarding approach here. No, because sometimes the false scarp is the most meaningful thing in reverse fault, as you have been showing. I mean, of the main ones. So we should be going more far field and try to get more data from that approach.
Okay. Cool. Well, it's been good talking with you, and I have to get on to some other projects here, but I hope you had a very successful course, and I hope you are okay with all that deep snow at your house.
They are gone now. So thanks again for your very, very insightful, clear, and thanks again for your low speaking English, which I think was very appreciated by the participants. So we'll stay in touch. Jim, thanks again for being here today.
Vaya con Dios.
Bye-bye.